Welcome everyone. Welcome to this new Datadog On session. This time we are going to be talking about gRPC. Datadog is a series where we invite engineers, designers, product managers working on Datadog on a daily basis. And we invite them to talk to us about a piece of technology they use, a language, a process, even a design process as well. We've done a few. If you want to watch any of the previous episodes, you can go to our website, datadogon.datadoghq.com, and you can see all the recordings there. A little bit of housekeeping. So you will see on your Zoom client, you have a couple of buttons. One says chat, one says Q&A. If you want to say hello, introduce yourselves, talk to other attendees, please use the chat window to do that. But if you want to ask questions to Antoine and Antonin, please use the Q&A button, because that's where we are going to be feeding all the questions. And at the end, we will leave about 50 minutes to answer as many as we can. We want these sessions to be as interactive as possible, so please do not be shy. And take the opportunity to ask those questions. So few words about Datadog itself. Datadog is a monitoring and security platform that helps companies improve security and observability of their apps and infra. That's what we do. My name is Ara Pulido. I'm a developer advocate here at Datadog. I'm also one of the co-hosts and co-organizers of the Datadog On series. So if you have any feedback about the series, anything that you want us to change, or any topic that you want us to cover that we haven't covered yet, please reach out. I'm happy to get any feedback. But the important people today to talk about gRPC are Antonin and Antoine. Antonin and Antoine were part of a squad that would form from several teams at Datadog to investigate gRPC issues for a while and then come up with a set of best practices for all of our engineering organizations. Antonin, do you want to introduce yourself?
Hello, so I'm Antonin. I'm part of the core resilience team at Datadog, and I'm mostly working on incident management and remediations and investigations.
And I'm Antoine. I'm a team lead for one of the networking teams here at Datadog, primarily focusing on improving service-to-service communication, service discovery, and these kind of issues.
Great. Thanks for joining us today. So one of the things that we like to do always on these episodes is to discuss a little bit about the scale that we run on, because some of the decisions that we make, some of the problems that we encounter are sometimes related to the scale. So just so you know where we are, so Datadog has more than 80,000 customers. We are a monitoring company, so we gather data, telemetry data from those customers. That's up to millions of hosts. That translate on trillions of data points per day that we need to ingest and process. And we also have Datadog is composed by hundreds of services, but Antoine will give some more details about some specific about services, because that's where we are going to be talking about today, gRPC. So Antoine, for those who may not be that involved with that project, do you want us to give us a quick intro what gRPC is?
Yeah, sure. So gRPC is a cross-language remote procedure call framework that helps connect network services with each other. It can be used to connect microservices within and across the data center, as well as web and mobile devices on the internet. So today we will mostly focus on using gRPC within the data center, because this is what we use it for mostly at Datadog. gRPC is more than just a simpler way to define and call network services. It embeds features such as advanced service discovery, client-side load balancing, connection management, health checking, security, and it has a very flexible, pluggable architecture that allows integration with observability products such as Datadog. We use all three major implementations for our backend services: Java, Golang, and C++. The latter mostly through the Python wrappers. The Datadog infrastructure is composed of hundreds of services that interact with each other, either synchronously or asynchronously. For asynchronous communication, we mostly use Kafka, and it's a large chunk of the traffic that we have internally. But for synchronous communication, we mostly use gRPC. And the overall gRPC traffic within Datadog is large. It's in the order of hundreds of millions of requests per second, flowing between tens of thousands of pods that run inside our Kubernetes infrastructure. So some of this talk applies particularly to environments running in Kubernetes, but a lot of it can also apply to other environments. And so at that scale, we had a chance to experience firsthand that configuring gRPC correctly for all use cases is quite challenging. So what is it that gRPC actually does? So the goal of using gRPC is to make communication between network services as seamless and transparent as possible. So when defining a gRPC network service, users are just implementing an application interface that is registered through a gRPC server. And then when calling a gRPC service, users just call that application interface in their own application through a gRPC client. So from the point of view of an application developer, calling a network service just looks like calling a function. But in reality, that function can be implemented and served by a different process running on another machine. Or another pod if you're running in Kubernetes. The details of how the RPCs are carried over the network are abstracted away by the library. And those abstractions make distributing applications across the network easier, which is very important for large systems of many services operated by many teams, like the system that powers the Datadog product. So even though we are going to talk about some of the pitfalls that we run into here, still gRPC has been a key piece of technology that allowed Datadog to scale to its current size, and it mostly delivered on its promise to making network programming more transparent and easier for application developers. Okay, so what is it exactly that gRPC is actually taking care of? So besides serializing payloads, it is mostly load balancing requests across a set of endpoints. This lets service owners scale out their applications when load exceeds the capacity of a single instance, which is often the case for a big service like ours. It also makes the service more reliable in the case where a replica fails. On this diagram, you can see one service instance running a gRPC client that communicates with 4 server instances. But in reality, in practice, a given gRPC service usually has many clients. So sending a request over the network happens roughly in 4 phases. First, gRPC queries the service discovery system to obtain a list of network endpoints that implements the service. At Datadog, we use Kubernetes headless services coupled with DNS for our service discovery. We will get into more details of why we make that choice later in the talk. Second, the gRPC picks a host from that list to send the request over. This is the role of the balancer, which is the internal gRPC component responsible for load balancing. Then it sends the request on the wire. gRPC uses HTTP2 on top of TCP as a transport protocol, and Antonin will explain further detail how gRPC optimizes the use of TCP connections across requests, which is good for performance. And then applications receive the response and forward it to the application. Now, when distributing applications over the network, there are a few failure cases that need to be handled correctly by applications. The network is unreliable, or can be. There can be delays in packets, latency can increase, things like this. And also, server instances can come and go at any time. So load balancing needs to take these problems into consideration so that they do not appear in the client application as much as possible. It frees application developers from handling some of those concerns. This makes programming systems that use gRPC easier. Some of those problems are handled by the library. And in gRPC, this is partly done via features called keep alive, health checking, that Antonin will go into further details later in this talk.
Great, fantastic intro. Thanks for give a high-level overview of what gRPC. And obviously, you said some clear thing that on a distributed system, we all know things can go wrong. So I guess, and this talk is a lot about some of the issues that we found over some months and years. So how we are able to observe gRPC to debug some of those issues.
So gRPC comes with, so we offer tracers for gRPC that can be injected in clients and server via the gRPC interceptor interface, which every request flows through. And it's one of the main extension mechanisms that gRPC provides. And then Datadog can report golden metrics for the service, like latency, error rate, throughput, and you can retrieve spans in APM. So here you see those graphs. We'll reuse some of them in the presentation for some of the investigations that we did. This is something that Datadog engineers use on a daily basis, and probably some of our customers too. Here you can also see a span. So if you're using APM, this integration also provides you with this kind of views that help you see requests flow through the system. And the last thing that we provide is synthetics. So this allows users to define black box monitoring for their gRPC service. You can simply define probes that should be sent to your service regularly. And if there is a problem, the synthetics product will make it easy for you to detect it, regardless of like other problems that might happen within the system.
Good. Thanks for that intro. One of the things that when we were preparing this session that we thought was going to be super useful for attendees is that now we know high level what gRPC is, but during the session we are going to go deep on some of the issues, and it would be a little bit tricky to go through those issues without explaining some of the internals of how gRPC works. So Antonin has prepared a little bit more deeper intro to gRPC, focusing on those internals that will be very, very helpful when we discuss some of these issues.
Yeah, exactly. So to try to understand the incident we will talk about, understanding how gRPC is implemented is going to be useful. So first, the implementation details I'm going to talk about is the transport. gRPC is using HTTP2 as a transport. One of the main difference between HTTP1 and HTTP2 is how they manage parallel connections. With HTTP1, if you want to do multiple queries at the same time, you will need to create one TCP socket per query. While with HTTP2, there's a streaming system inside the HTTP2 client, and this allows the HTTP2 client to multiplex multiple queries in a single TCP socket. So this way, you will be able to have 100+ parallel queries reusing the same TCP socket. And this is something that you can see if you capture the traffic between gRPC server and client using TCP dump, and then looking at Wireshark. You decode the traffic as HTTP2, and you will see the details of the gRPC calls, and you can see that everything is going through the same TCP socket, so same source port and dest. And you see the multiple queries. So here we have the first gRPC query with the headers and data using the HTTP2 stream ID 3. The second query is going to use the stream ID 5. So one interesting detail is gRPC only use odd stream ID. A stream ID 2 or 4 is illegal and will be refused by a server. And then you will have the answer, which can be in any order. So here we have the first answer, which comes in the second position in the same TCP frame as a second query. So that was for the transport. And one of the abstractions that's provided by gRPC when you want to create a connection to the server is the channel, which is one of the major abstraction of the gRPC. So a channel will have multiple states. It will start in a connecting state and it will switch to a ready state or a transient failures depending on its life cycle. And when you create a channel, you will provide a target, which can be an IP or the domain name. And then here I'm assuming we are using round-robin balancing. In this case, the channel will create multiple subchannels, one subchannel per IP. And those subchannels will have the same lifecycle or semantic as the channel. They will have a connecting state, and they will switch to a ready state when it managed to get the connection to the server. The subchannel will create the HTTP2 client, which will then create the TCP socket, which will then start the connections to the gRPC server. Once the TCP uncheck is done and the HTTP2 uncheck is done, the server, the TCP socket will switch to an established state, and the subchannel will switch to a ready state. And since you have at least one subchannel ready, the channel will switch to a ready state. From that point, the channel will be able to handle queries, and they will go through the ready subchannel. So it's interesting for the following incident to try to understand, like, to map the socket state with the subchannel state. So when we created this subchannel in connecting, the socket will be in a SYN state. And if the TCP socket is established, then you usually have a ready subchannel behind it. And then transient failure and shutdown will match TCP close, a socket closed, or a socket in a thin wait, and so on. So, yeah.
Cool. So I think that's enough to know, that needs to be known to follow the fun part of the talk, which is some of the real examples that we faced at Datadog. As we mentioned at the beginning, Antonin and Antoine were part of a squad that from engineers from different teams that gathered together for several months to investigate some of the gRPC related issues that we had at Datadog, and trying to come up with best practices for all engineering teams to follow. So we are going to go through 4 of those. First, we will explain the issue and also the best practice that came along with it. So let's start with load imbalance, Antoine.
Okay, so the first issue that I'm going to talk about is about how to properly load balance between instances. And as we'll see, some of the default behaviors of an infrastructure like ours are not always the best ones. So here is an example of what happens when we have 100 gRPC clients that send traffic to 10 gRPC servers with the default setup. Each gRPC client sends roughly 100 requests per second. So the top graph shows the number of requests received per pod. And as you can see, they are not balanced. Some receive a lot, others very few. This is what we call load imbalance. And this isn't just a theoretical problem. In practice, it leads to varying CPU utilization, which is bad for costs, as in most cases, we reserve about the same capacity for each server instance, and we cannot really adapt capacity to incoming load. So here we'd have to provision all instances for the maximum amount of traffic that happens. This is really not great. Ideally, we'd like each pod to get a fair share of the traffic. So to understand why we see this kind of imbalance, we have to understand a little bit about how Kubernetes services work. So for inter-service communication, Kubernetes offers the service object that claims to ease load balancing, and it does in many cases is the right thing. But so by default, it uses cluster IP. The way cluster IP works is that it takes care of load balancing. It creates a virtual IP for the target service and configures a proxier that will randomly assign each connection to a server instance. So as a result, gRPC sees a single IP address out of service discovery as the server for the right part of this diagram. It sees a single IP as a server, so it opens a single connection to that single server and sends all its requests to it. Why is that that this results in such imbalance when there are many clients? Remember that on the previous slide we had 100 clients. So wouldn't the 100 clients end up being evenly spread, given that Kubernetes proxy randomly load balances connection? Turns out that so the intuition behind this problem is that if you roll a 10-face dice, let's say 10 times, it is very unlikely that you get one number of each face. It would mean that you were lucky enough to hit a different face each time. You may think that distribution evens out if you roll out the dice many times, and you'd be right, in fact. But the number of times you need to roll the dice is very large in order to get reasonably uniform distribution. If you roll the dice 100 times, you get a distribution more like on this graph, which is still quite imbalanced. And in fact, this matches what we saw in the Datadog graph that we saw earlier. Rerolling doesn't really help. You end up with another uneven distribution. So the first thing that we need to do in order to solve this problem is to switch to a headless service. With headless services, Kubernetes returns all available IP addresses directly from service discovery and leaves load balancing as a responsibility of the client. Now, gRPC has awareness of each server instance, and each client can take care of better balancing requests. But this isn't really enough because by default, gRPC also picks a single instance and sends all requests to it. This is what is called the pick first balancer. So we changed the way Kubernetes works, but we also need to change the way Kubernetes was configured. Now we also need to change the way gRPC is configured. So the change that we need here is to switch to the round robin balancer that luckily ships with gRPC, and it guarantees that each client will themselves spread their requests evenly across server instances. So by enabling these two changes and looking back at the graphs that we had earlier, this is with rolling out Kubernetes headless services and the round robin load balancing. We can see that requests converge to be about 10,000 per second per pod, and this becomes much easier to size the pods correctly.
Great. It's great to see how that graph is pretty nice to see how it goes all to the same place. One question that I had when I saw this graph for the first time was this feels like this is going to be an issue for everyone using gRPC on things like Kubernetes. Why then it's not round robin the default load balancing algorithm in gRPC? So
I didn't make the choice to not choose round robin by default, but I can only guess. But I think there are many environments in which gRPC can be used. And remember at the beginning that I described that it can be used within the data center, but also from outside the data center from mobile applications and things like this. So in that case, usually you have a load balancer in front of the system. And in those cases, this default setting actually makes more sense.
Makes sense. Thanks. Let's move to the next use case or issue that we investigated, the IP recycling problem. Probably attendees who are running on Kubernetes may already have a hint of what this means. So Antonin, what's the IP recycling issue?
So yeah, it's an issue we started to have when we switched to Kubernetes. So in our example here, we have multiple Kubernetes deployment for our gRPC servers. And we usually split our services by shard, for example, for client isolations. And in this case, we have shard 1 and shard 2, and our gRPC client is connected to the shard 1. When we trigger a deployment, you have a rolling update that started. So the server will shut down, it will terminate the connection, and the server's IP will be put back in the free available pool of IPs. However, the client is still trying to connect. Like the first thing that the client will do is immediately try to reconnect reusing the same IP. And what can happen is a completely random servers grab this IP, and you end up with the gRPC client trying to connect to a server that's maybe not listening to the port you're expecting. In this case, you're going to have connection error, or it might be a completely different server. In this case, you're going to have query errors. But one of the most critical things that could happen is connecting to the wrong shard. So in this case, the shard 2 managed to grab the IP that was assigned to the previous shard 1. And in this case, you can start sending your data for a customer in shard 1 in the wrong shard, or you start to get answers from shard 2 while you were expecting this to be shard 1. And this can lead to data leaks or data loss, and is usually something that's rather critical and a pain to manage. So what did we do to try to solve that? Is we implemented a release interceptor, which is going to add an HTTP2 header to every query. So this HTTP2 header will say, I want to connect to the shard 1. And this way, the server will be able to check if it is the intended target. On the other side, you also have the answers from the server that will have HTTP2 header saying this is a server from shard 1. And this way, the client will be able to double check that it was connected to the right server. And this way, when you have the IP recycling issue and you're connected to the wrong shard, then the server will refuse the query because there's a mismatch. Or if for a reason the server doesn't implement or doesn't check this, the client will be able to check either by checking that the HTTP2 header is present or is matching what the shard it was expecting, and maybe refuse the query in this case. But it's better if you can avoid altogether to send the query. And this is something that can be done using the health check system gRPC. So the client will send a health check request. The HTTP2 header will still be added to the health check request. And this way, if the health check fails, the channel will basically stop being ready, or it will stop accepting queries, and the gRPC client will stop sending queries to the server altogether. So yeah.
Nice. This looks so we were saying that your work produce a set of best practices, but this seems that it's not only a set of documents of best practices. This also comes into the tooling side of things. How is this tool used by the engineering teams, or is it deployed to the cluster or something else?
So the best practices are built in a standard library. We build a shared library, so people who want to use a gRPC client or create a gRPC server can just reuse what we provide. We provide some way to customize it, but usually we say, okay, this is the parameters we want to set so that everyone will match with parameters. And the release interceptor is provided in this shared library.
makes sense. Good. So let's move to the next sample. This time about proper scale out detection, something that scaling out is one of the biggest reasons why people move to VMs first and containers then, and using something like container orchestrator like Kubernetes. So what's this proper scale out detection issue, Antoine?
Yeah. So let's see. So sometimes load starts exceeding the capacity of each server instance that is running a given service. So when this happens, service owners typically want to add more instances, right? So here on this graph, you can see that the server pods running went from 10 to 12. But below, you can also see that the number of requests received per pod didn't change. And this number stays at 10,000 per second. And it looks like the new pods are not actually getting any traffic. And this is very annoying, especially because scale-ups are usually something that people want to be quick, as they may be a consequence of a traffic spike that must be absorbed. So the problem that we discovered is that the DNS resolver that ships with gRPC does not actively monitor the results of DNS, even when the TTL of the entry has expired. And instead, by default, gRPC only forces re-resolution when at least one subchannel of the client is closed or changes state. So armed with this knowledge, the solution one of the solutions is pretty obvious. And one thing that we advise as a best practice is to actively make server connection churn clients by setting the max connection age to 5 minutes. The 5 minutes strikes a good balance between churning TCP connections, which costs a little bit to both clients and servers, by the way, especially if they do TLS, for example, which has a costly handshake, and re-resolution speed. It's good because it's a server-side solution. So as a server, you can protect yourself from clients that may not re-resolve by just setting this configuration. So here on the graph, you can see that after scaling up, within the first few minutes, the load converges to use the new instances. That's good, but we can do better actually if we control the client, and we also ship with our default library with a custom resolver that we call the polling resolver that actively monitors the results of DNS, and therefore scale-ups can be picked up in a matter of seconds, actually, more like 5 seconds, which is very appreciated by service owners.
Cool. So it's more or less putting a safety net on both sides. First on the server side, just in case the client is not using the polling resolver, but also improving the client side if they do.
Right.
Cool. Okay, the final one today is the silent connection drop. So after this one, we will be moving to Q&A. So please use the Q&A button. You don't have to wait until the end to ask your question. You can drop them there. We will pick them up afterwards. So the silent connection drop issue, what's that, Antonin?
So yeah, well, in our incident, we start with a basic setup of gRPC clients connected to gRPC server. Everything is established, the socket is established, and the channel is ready. You're going to have a silent connection drop. So what do I call a silent connection drop is when you're on a cloud provider, for example, and you, for example, you have a hardware issue, and from that point, every packet that will be sent through this link will do nothing. So everything will be black hole, basically. And because of that, the socket is not going to receive a FIN or a hack from or reset from anything. So the gRPC client will still try to use the subchannel and the socket because everything is established and nothing happened yet. So the query will be returned, will create a stream. The stream will write the payload in the socket buffer, and then the socket will try to send the packet. And for example, imagine you have a super short timeout of 5 seconds. The gRPC client will timeout the query, but that doesn't mean that the stream or the payload in the socket will be removed. So the TCP socket will start entering in a kind of a busy socket state where it will keep retransmitting the payload because it didn't receive any hack or reset or anything from the server. And you can see those busy sockets in details using, for example, SS, where you see the socket is established in the state column, the number of bytes that are unhacked in the send queue column, and then the details on the TCP timer. So if you have an on timer, it means that the TCP socket is retransmitting, and you have the time until the next retransmission, so 204 milliseconds here, and the number of packets that were already retransmitted. So we have our client that, from the client perspective, everything is fine, and it will keep using this subchannel, and you will have more and more streams in your subchannel and more payload in the socket. So eventually, we reach some kind of limits. We have a default 15 retransmitted packets in Linux. And when you reach this limit, the socket will return an error, a timeout. And the subchannel will pick this error and will switch to a transient failure state. And from that point, the gRPC client will stop using this subchannel. So we usually have more than one gRPC server, and you can have this kind of setup where a specific connection is impacted while others are fine. And all queries that are sent to the impacted subchannel will timeout while others are successful. And in this case, we'll have basically a 50% context deadline exceeded, errors. And this is something we saw on production. So in this graph, you can see the 15% timeout on the gRPC client side. And one thing that's interesting really is the 15-minute time frame. Like we did nothing, it recovered on its own. And if you see something similar with a 15 minutes time frame, that's usually a good sign that you're dealing with some kind of TCP retransmission timeout here. So what can we do to try to solve that? Is we use, or at least indirectly, we will use the gRPC Keep Alive feature. So gRPC Keep Alive is when you create a gRPC channel, you will have the possibility of providing Keep Alive parameters with the time and timeout. So in our example, we're going to say, I want 1 minute Keep Alive and 20 seconds timeout. So what happens is when you have an ongoing query and the server didn't send any payload after 1 minute, the client will send a HTTP2 ping and will expect the server to answer with a HTTP2 pong within the 20 seconds. So one interesting and a bit obscure side effect of setting gRPC Keep Alive is that it activates on the socket the TCP user timeout option. And it will reuse the timeout value that you're providing as the value of the TCP user timeout. So what does this socket option do is it's basically a Linux-only TCP socket option, and it will limit the time spent in the retransmission for the socket. I'm simplifying a bit, but basically, because we are setting the TCP user to 20 seconds, the socket will not will pick the minimum between the 15 retries, so which is 15 minutes, more or less, and the 20-second TCP user timeout that was set by the gRPC keep alive. So in this case, it will cut down the time spent in the retransmission from 15 minutes to 20 seconds. And so that's rather interesting because you have basically two systems that are contesting to close the socket. And you are, on the one hand, you have the TCP user timeout that will generate the e-timeout error on the socket. And the gRPC client will also, on its side, try to close the socket because it didn't receive the ping in time. So one thing that you need to be careful of using gRPC keep alive is the max ping strike system. So the server has some mechanisms to protect itself because HTTP2 ping is not cheap. Like it's still a HTTP2 request. And if you have thousands of clients doing a ping every seconds, it means you have thousands of HTTP2 queries to handle per second. So this is why by default, the gRPC servers are configured to have a minimum ping interval of 5 minutes. And if it receives a ping within this limit, it will give multiple strikes. So one strike per ping it receives before the 5 minutes limit. And when it reaches the third strike, the server will close the connection with too many pings, errors. It will send a go away and close the TCP socket. So all ongoing queries in the subchannel will be closed because of that. And so at the end of the day, we only need the TCP user timeout system. We don't really need the gRPC keep alive itself, but we still need to set the TCP user timeout value, which is done by setting gRPC keep alive. So that's what we implemented in our best practices is you saying you need to set the gRPC keep alive to 15 minutes. So it will never trigger because most of our queries are less than 1 minute generally. And trying to explain, yeah, you need to set the gRPC keep alive and to have this really high value because we're interested in the TCP user timeout. And this is something that's definitely interesting because I think a lot of times in the past and before the squad, a lot of people activated this and saw a better behavior and thought that the gRPC keep alive fixed their issues when in fact it was the TCP user timeout that made the situation better for them. But because it's rather obscure and I mean, it's documented, but you need to really read between the line to understand what's going on. So yeah. And that was for the silent connection drop incident.
Nice. Indeed, very, very secure one. One of those things that once you learn it, you never forget because it's so tricky that it's something that I'm sure you will never forget. Okay, so we are going to Q&A first, some takeaways. So what would you like people to take away from this session?
So yeah, one of the takeaway I will say is like even if we focused on a lot of incidents, doesn't mean that gRPC is hard. It's just that distributed systems are hard, and as soon as you're talking through the network, you're gonna have those kind of systems. Like most of the issue we talk are kind of network related, and gRPC provides a lot of tools to try to tackle and fit your situation. So you need to understand and to really read what gRPC provide. So sorry to see what could be what gRPC could provide for your needs, basically. And that's also an interesting point. Like for a long time, we didn't really tune gRPC configurations or did the minimum, and it fit our needs. And even with scales of 1,000 instances, the kind of default configurations of gRPC was fine for a long time. And it's only now that we're really hitting the limit of we need to fine-tune the gRPC to solve all the issues we have.
Good. Thanks both. So we are going to go for questions now, but before, if you think this type of problems are interesting to solve, you want to join Antoine and Antonin in discovering weird networking issues. We have a lot of engineering options open, so go to our careers page and have a look. I'm going to start. I have a couple of questions also ready, but we will start with the ones from the audience. The first question from a known guest is, how do you implement or integrate the polling resolver? Or implement/integrate?
So I can take this one. So Datadog has, as I said at the beginning, we have some applications written in Java, some applications written in Go, and some applications written in Python. So we actually have sort of mono repos. We're actually consolidating our different code bases, and this is where we provide those libraries. It's basically a resolver. It implements the resolver interface that gRPC provides. So you just have to switch it, and the batteries included versions of gRPC that we ship actually use it. We don't have it for Python though, so because it's a bit more difficult to integrate things via, like it would basically require us to write some C++, and you know, like it's more difficult to do, especially it's more difficult to bundle.
Good, thanks. The second one is fairly specific. I don't know if you will know the answer, because it's like reading all. So I'll read the questions, and feel free to say you don't know, because I've experimented black hole and mitigated with keep alive settings. It globally fixed the issue, but I still have dozens of unavailable error at some points. After how many times the buggy subchannel is removed? How do you handle retry on this case?
So it will depend. I'm curious, like question, like, are you using Big First or round robin? Because for me, like if you have an available error, can happen if you have a ready subchannel, but you're using health check, and the health check like failed for a specific service. So it can lead to it can lead to unavailable errors. But globally, like the subchannel, after how many times the buggy subchannel is removed?
I think you actually answered this one during. So the question was asked before you mentioned the 20-second TCP user timeout, and this is basically, I think this is basically the answer. I mean, it's not a number of times, but it's a time frame actually that becomes much shorter.
Yeah. It just like for me, like the unavailable error is kind of different. Like I was expecting a deadline exceeded or a timeout error after the 15 minutes, which is kind of different case here. But globally, like a bug subchannel is only removed when you have a change in the resolver, like you have an update in your resolver that will remove the IP from the pool. In this case, the subchannel will be close to this to the previous IP. While the IP is still advertised in the resolver, you will have a subchannel. It might be in a transient failure state. It might be a ready state. It will depend on does it manage to connect to the gRPC server or not. It's so one thing that you could do to try to get more information. Sorry if I take too long to answer the question, but something that you could do that we don't really talk about this during the talk is to use channel Z. So channel Z is a way to get the channel state in the gRPC. So you will be able to see if you have a subchannel that is in the state of the subchannel, and yeah, maybe this way you will be able to see to get more information about what's going on.
And in fact, Antonin is currently working on integrating Channel Z with the Datadog product, which we don't have an ETA on when this will land, but I think this will definitely interest people that use gRPC and want to have better insights into the channel state.
Yeah. Nice. Okay, so we don't have more questions from the audience. We still have time, so feel free to drop your question there. I'll ask a question in the meantime to make sure that we give enough time for people to think about the questions or follow-up questions after getting a response. My question would be, would you recommend gRPC for any application side, or are its benefits only worth it once you've reached a certain scale in terms of team size and also number of services, for example?
So I can take this one. I would recommend using gRPC. I mean, we've had very good experience with it. I would recommend it for basically any time two applications need to communicate over the network. The first benefit that you will get beside like load balancing and more advanced things like this is simply that it's just less boilerplate. Like the integration with protobuf makes it very easy to define a service and define it and call it through a client. So I would say, you'll probably not run into these kind of problems for a while, but you will still benefit from the more like basic features.
Cool. Okay, so I have a final question, and we will leave it here if we don't get any other questions from the audience. We are almost at time anyways. But one thing that I'm curious about is, have you seen a decrease on gRPC related incidents since you created this set of best practices and the tooling, related tooling?
Yeah, I can take this one, I guess. I think the problem is with best practices we have, it can take some time to propagate, and we need to do some advertisement inside the company. One positive thing is when people comes with an issue we are already aware of, it's much faster to say, hey, we already know this issue and this is how you fix it. And this way, it's also a way to say, hey, we have this shared library with all the batteries provided, so you can just use this now. Yeah, I would say like the number of gRPC incidents, that depends. Like it comes and goes. So I honestly, I think we have less incidents compared to before. Might be because of the best practices, but yeah, it's hard to say. But I think we're definitely in a better place now with all the best practices and the knowledge we have from the gRPC, how gRPC behaves, and
I would add also that Datadog is a fast-growing company, and the scale at which we operate is constantly expanding. And some of the problems that we're seeing now, like we see services that have too many clients, for example. This is something that you don't have when you have a small infrastructure, and now it's becoming a problem for some of the biggest services at Datadog. So this is an example of like new problems that we have, and we expect that we will have new problems as we get even bigger.
Cool. So we had another question from the audience. Do you have Android or iOS mobile clients connected to backend services?
No.
No.
No. All of the gRPC client server we have are really within data centers on Linux on the instances we manage. So.
And I'll also add that a lot of the things that we talk about don't really apply in the context of like an iOS or a mobile application connecting to a remote service on on the internet. So
complete different situation indeed. Okay, so we are at time and we don't have any other questions from the audience. So thanks everyone for attending. Just so you know, in a few days, the recording of this episode will be available on our website on datadoghq.com. So feel free to pass it along, colleagues that might be interested. And thanks Antoine and Antonin for sharing your knowledge. I've learned a lot during this episode, so thanks a lot. It's super interesting to see some of these networking issues and how you solve them. Thanks a lot.